Example 4. Projectiles. A projectile is sent off with an initial speed of 350 meters per second and clears a fence 300 or 3,000 meters away. The height of the fence is the same height the initial height of the projectile. If the distance of the projectile traveled is given by d equals this equation, find the interval of possible launch angles to clear the fence. Now first, as just a review, this is a real-world problem, and so real-world answers are going to be first quadrant, like positive answers. Secondly, we could just graph this or in-solve it to figure out the answer. Here's what it's given to me. 350 is the v sub 0 here. And so when I substitute this in, I'm going to put that in parentheses so I don't mess up the squared there. And the distance is 3,000. And I want it to clear. So I want this to be greater than the distance of the fence. So here's this. Find the interval of possible angle that will clear the fence. I actually want this to be greater than or equal to. So that's the way I'm going to solve this. So again, you could go graph, this is F1, this is F2, and you could search for the answer. That way you could in-solve something like that. But I'm going to do the algebra real quick. So we have this. The first thing I'm going to do is get rid of that 9.8. So this is 350 squared sine 2 theta all over 9.8. And what I'm going to point out is to really clear the fence, like if it was equal to, it would hit the top of the wall. So just to be safe, I'm going to put it the symbol that way. That's what I'm going to do here when I solve this. Okay, so the first thing I would do is get rid of this denominator. So let's multiply both sides by 9.8. So when I multiply this by 9.8, let's see here, menu, calculator, whoops, what am I doing? Menu, add a calculator. So we have 9.8 times 3,000. And I get the value. This is going to be 29400 is less than, and we could simplify this out, but I'm just going to leave it here for a second. 350 squared sine 2 theta. Okay, now how do I simplify this? Notice that these are multiplying times each other. So the opposite of multiplication is division. So I'm going to divide by 350 squared. And that will get rid of that. So now I'll go here, divide by 350 squared. Because of PEMDAS, it'll treat this in the right order. It'll do the 350 squared first. So we get 0.24. So now we know that 0.24 is less than or equal to sine 2 theta. And we're going to be solving this in radians. So let's make sure our calculator is in radians, which it is. It'll throw you off if you're in degrees. So now, how do I get rid of sine? Well, I would do a inverse trig. So if I go trig, inverse trig of 0.24, I get this value. I get, again, 0.24. So this is now, this is talking about right here, the length, if you will, and this is trying to find the angle. What I did here, let me write it out so we have it, is I took the inverse sine, and coincidentally it gave us the same value. And here, when I take the inverse sine, this leaves us with, that leaves us with 2 theta. So now I have, come up here with this, 0.242366 is less than 2 theta. And we divide this by 2. And I find out that, I'm going to divide this by 2, I get that theta has got to be, it opens towards theta. So let me write it over here so we don't get confused. Theta has got to be greater than 0.121183 radians. So that's our value here that we're looking for. Now let's go over to the graph and let's check it that way. So I'm going to do Control Doc here. I'm going to go add a graph. And just like I told you before, I'm going to say 3,000 as the first equation. The second equation is going to be this 350 squared times sine of 2 theta which we're going to do x in the place of theta, and this is one big great fraction. All this is over 9.8. Now I know the height that's going to cross that is 3,000 because that was the first one, so I got to go higher. I'm just going to say 3500 like that, and I look for where it crosses. I was looking for its real world, so I'm going to be trying to, sorry, I can't get that really to shift. I'm looking between these two intersections because this is the value where it clears the fence, and this is where it's too low. So I'm going to go Menu, Analyze Graph. I'm going to look for intersection, and see that was that first answer we got. And so the wall would have to be between there, and it could not go past the next one because since it's real world, let me do this for you. I'm going to change this to a negative 1,000. Whoops, negative 1,000. And I'll show you the, or yeah, 1,000. Let me show you the problem. You see how this would be the ball going up and going down. So really, anything after this is no longer real world. So we have two answers, and the value's got to be between there. So I'm going to come back and add this in. So from the calculator, we saw that it's got to be greater than this angle, but yet less than 1.45. So I'm going to list this as my answer values here. And I'm getting this from the graph. This is in radians. Now there's one here for you to try, and notice that they put the same value. And they put it equal to, which I'm not as particular on that. You can argue over that because if it hits the top of the wall, you don't know necessarily what's going to happen. And so here, anyways, this would be the launch angle. This we got from the calculator. That I got from the calculator. So I will put that there. This we got from algebra. Could you get both from the calculator? Yes, we could. But I just want to deviate between those two so you know what's going on.